Yo, what's up? What's up? What's up? Welcome back. Today we're working on my image to ascii neural network. So the idea is we have a picture, see on the left, we want to turn it into text. See thing on the right. No real good reason, just seems like it would be fun. And we want to do this like the best job we can here. And so the naive solution is to just look at the brightness of each sample that we take when we turn it into a character. But that looks kind of like shit, right? Here are all like the options for characters that we have. And we like look at the brightness of each one and we say, which one is like the closest to the thing on the left? And that works like, kind of okay, right? Like we can see like if we click on something brighter, we get a brighter character. If we click on something like really bright, we get a really bright character. If we click on something dark, we get something darker. But like the overall thing doesn't look good unless your character size is like really small. And so what we're aiming for is to get sub-glyph accuracy, which we've kind of got to the point where we get something like pretty decent, right? This is no AI involved right now, right? All this is doing is we have like taken a glyph, blurred it a little bit, kind of like skewed that with like the brightness, and we basically say for each character we look at the blur, we like compare it with the sample image, and if it's close then we like it, and if it's not close we don't like it. And that's what we worked on yesterday. And so we're at the point now where theoretically this is like the answer, right? Except that it's slow as shit. It's really slow. To compute like this image on the CPU takes around like 6-7 seconds at this resolution, which is like insane. That's like unreasonable, right? Say we wanted to like render a video and apply this filter on top, right? Like that should be, we need to be fucking fast, right? Like if we wanted to do like at 30 frames a second, that's like, wait, we have like 0.3 millisecond or 0.3 seconds, 33 milliseconds to do it. And so the idea here we're thinking is that training a neural network to predict the correct label for us should be faster than doing it ourselves. Hand wavy, right? And you might be able to like extract meaningful features out of the data and come up with like a rule set that is cheap to compute, but still gives you something that's like approximately right. Maybe not perfect, right? But what we have isn't perfect. What we have is like fucking random. We just kind of like twiddled some numbers until we got something that looked like kind of reasonable. And so as long as like the neural network predicts something reasonable, we should get something right. You could say, well, what if you didn't want to use a neural network? How else could you like do this by hand? And so let's like think about this a little bit, right? There's a like, say we have like a 5x5 grid as our sample, right? So this is like we're taking a sample from an image, we're taking 25 pixels from it, and let's say that there's like the number 1 just sitting here, right? This could be pretty well approximated by like the character 1, assuming that the font looks kind of like this, right? If we were to do this by hand, you have a couple options. One is like pre-computing in some way, right? So say we tried to like make like a lookup table for all possible options, and no matter how expensive the computation process is, it doesn't matter because we'll just pre-compute it and we'll store it and we'll answer it. We'll look it up. But say you have like, images are like 256 pixels, so each pixel has 256 options, and if you want to like check every single combination here, you have like 256 to the power of 25 is like how many options there are. So you'd have to store that many computations. That's unreasonable. Well, what if you like quantize this a little bit? Let's say we have like 4 pixel values. We quantize this down to like 4 things. That's still a lot of fucking options. And like the other option is, okay, so we have like, how many characters do there possibly be? What if we just did the comparison for every character for every sample? And that's what we're doing right now in our training label setup. And it turns out that that's like expensive as fuck as well, because we have like, what is this, like 1,500 characters in our font right now that we're like choosing from, and that's just like expensive. It's like, well, you can purchase the character set, but then that doesn't work as well. So all of that's like kind of like the justification for why AI, right? Otherwise you might think like this is a fucking useless project, and it kind of is, other than for speed. And so what we've done so far is we've kind of like trained a sample neural network, where basically what we did was we limited our character set and we limited our labeling process pretty aggressively. And all we did was we said like, okay, we have like our pixels, and each of these is like fed into our neural network. So each one of these gets their own input, right? Boom, boom, boom. So here we would have like 25 inputs here. And each input is connected to each output like directly. So if we have like our initial example only had 4 characters, and we only looked at brightness. So we said like this is like the character space, and this is the character colon, and this is the character A, and this is the character add. And so this is like kind of like increasing in brightness approximately, and we basically just say, okay, we're connecting this to each one, boom, 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 and we're gonna like make some rules that are essentially multiply each of these lines as like a multiplication, and theoretically, like you don't need any like middlemen in here to like try to extract like more useful information. You can just look at the brightness of each pixel and directly deduce which one of these is right. And maybe you like weight some of them higher, right? So the first thought here is today's plan is to try training our new metric that we came up with yesterday, that's this, which is like much more complex than the initial brightness. Try training that with our initial model, see how that works. Compare the performance of our initial model with like manually creating the labels, and then try some ways to improve it, right? This metric is like pretty clearly a something of the order of, or sorry, not metric. This like neural network is clearly on the order of like number of pixels, which we'll call P, times like number of characters, which we'll call C, right? Approximately, right? Each character is being multiplied by each pixel. Sure. We could imagine, right? We could imagine that we could like inject something in here that basically we can just put like 30 nodes in the middle, 30. And so then we go to P times 30 plus C times 30 is the number of computations. And that should theoretically be way faster, right? Because we're going from like order of N time or P times C to order of like P plus C, which should be way faster. But you know, maybe that won't perform very well, and so we need some way to like benchmark, well, how fast is this, and how good is it, and how efficient is the train. And if we get there and we're kind of happy with what we see, we're gonna have to like start looking at, okay, where right now our training process is like really fucking stupid, like the stupidest it could be. We have one picture, and we just split that picture up into like a fixed number of samples, and then we just train. Every time we like do a training iteration, we look at that one image and we just look at it again and again and again and again and again. And like in reality, real neural networks have this tendency to basically like fucking cheat, right? So if you want this thing to work generally, you have to show it enough examples so that it can't figure out how to cheat based off the examples it's looking at. So there's a lot to look at there. There's like data sets, training and validation, like sampling, like augmentations. There's lots to look at there if we get there, but that's kind of like the general plan going forward. Probably we won't get all the way to the end of that, but that's what we want to work on. Yeah, so I think first thing to do is just to look at what we have so far. And let's do that. Train with our existing network. So I haven't actually like really tried this yet. I did run it just to like see that it still worked, but I haven't actually like looked at the results yet. So we have our training script. And let's just run it and see what happens. So we will delete all of these outputs that are just going like raw into this folder. I think I'm not deleting anything important here. Those are just output samples. And if we run it like this, what I noticed when I tried this earlier, I was just like making sure that nothing crashed. We never like move on from this first iteration. So what we try to do is we try to train. Here, actually, maybe we should open up the code. One sec. Let's pop it open. Got to give it a sec to get the environment shell set up. That's taking like way fucking longer than it should. Okay, we're in. So if we look at our training script, all he does is he runs this like big loop, and his loop is essentially zero out all of our gradients so that like basically reset some state, get our samples, which in our case is always the full image. So we're just gonna like every iteration we're regenerating the full image, regenerating labels for that image. We're then doing some like stuff to like make sure that it fits correctly into our network, and then we run the network. We check well, how good were we, and try to get better is like kind of these two steps. Like compute how much each thing in my network had an effect on the output, and then like please like improve it in some way. And we're basically saying like every 1,000 iterations, let's write out what we have right now and like print the loss. And you can see like as of right now, we still haven't got through 1,000 iterations, which is like a problem. That's gonna like we need to run for like thousands and thousands of iterations, and on stream especially, we don't want to just sit here and wait for 15 minutes for something to happen. So the first little trick we can do here is we can say, well, our training process is fucked, right? This won't extend later, but we could say that we only have one image, and so we don't have to recompute the labels every time we iterate. We can just do it once. And theoretically, you could pre-generate all of the labels for all the samples, but there's probably some sort of like disk space thing to think about there. But for now, we can just, or maybe not. Maybe the label computation could be done once, stuck into a text file, and then you just read those back. But maybe there's like a lot of samples. It's just something to think about there. But for now, we just say, fuck it. We only have one thing. All we want to know is the network like going to do something sane? And so if we just, oops, I have to copy paste this stuff out here too. If we just train with that, this should like speed up our iterations significantly, right? Like there, immediately got through 1,000 iterations. And so we can look at our sample image, which is this guy. This is what we're training off of, but a black and white version of it. And we can just kind of see, well, how are we doing? So I guess we should also look at this is like what we're shooting for. I can't open it in a new tab because the server that's rendering this is down, but it looks approximately like this, like, you know, pretty decent. And are we getting somewhere that like approximates that at all? It's not awful, right? We can see that there's a lot of the features in here have very quickly managed to figure out what they like should be, which means that our neural network is like, even like the dumbest version of it, which is just connect inputs directly to outputs, is learning something. Now, we don't know how well this will extend to other images, right? It could be learning something that's like very, very specific here, but it is learning like something. And we could maybe like zoom in on here and like, can we zoom in on here? And let's like take a look on like if these characters are resembling what we expect. So can we actually get to like a newer one? Because this says cranking them out. Iteration 22,000. And it's like, you know, that's pretty close, you know? Right, we're seeing like a lot of the same characters in here. We're seeing like this like @ symbol followed by this like little U thing and then a P, and then like these like squiggles and then like a greater than sign or a less than sign, less than equal, less than not equal. Right, we're seeing all of those same things right here. We can see like the same sequence. So it's learned something reasonably quickly if you ignore label generation. Our loss is still going down. Right, we see it started like pretty high. Numbers like slowly go down over time. Pretty good. It doesn't look like it's like capped out or anything yet, but again, it's kind of unfair because we're looking at like a single image. But that's starting to look pretty fucking good. And we should double check. I think we're supposed to be writing out our weights here. But I actually didn't save that part, so fuck. That's actually like an important part of this. So one of the things that we also have to do, where did that code go? Checkpoint? Somewhere we actually like wrote down the weights, which is like a very, very, very important fuck. So I guess we'll just rewrite that code because I don't know where it was. It was pretty simple. I guess that code I never got to the end of that. Never got to like the cleanup section of that, but it was pretty easy. So let's just quickly bang that out because we need to be able to save those so that we can compare them later, as well as like, it would be nice if when we're evaluating performance, even though it doesn't really matter, like the number of operations is going to be the same no matter what. It would be nice if like the output looked sane so we can prove to ourselves that what we're doing is the right thing. So what is it? Torch, save, weights. Saving and loading models. It was really straightforward if I remember correctly. Torch save, and torch load. Okay. So we'll just every 1,000 iterations, we will save our network state at i.stateDict. Boom. Easy. Which means let's just like quickly load or run the training process again, just in the background so we have something. And we can start looking at like, okay, well, if we wanted to like load these weights back, run them and benchmark them, what does that look like? So Let's get into that. So we can write a script that's like benchmark. And he is going to do something similar to what our training script did, in that he's going to load the network and then run it. So he's going to have like an argument parser that's going to take in the device we want to run in, what image we're going to run on, and then probably also we need to want to take in like the weights. Cool. Which means we need this guy. We're going to have like some sort of main function that takes in image, path, weights, and device. Cool. We also need to say that when we run this script, it's a Python 3 script. Linux knows what executable to run. And we have to throw in our if name is equal to main. We run main with the parsed arguments. I think it's something like that. Is that right? Yeah. Okay. So what are we going to do? We're going to run our network, which means that we actually have to get this network from somewhere. We need to know what the network architecture is. So that means that we actually have to... there's a few things to think about here. One is that this needs to be factored out into its own module so we can import from both the training script and the benchmark script. And it looks like it has like inputs and outputs that are defined by something external. So they're defined by the number of characters that we can write to, as well as the size of our samples. Looks like we've actually probably run long enough now. We have state dictionaries or anything, so I'm just going to kill this for a second. So I guess the question is, do we trust that when we run our second benchmarking script in the future, that we're going to end up getting the same number of characters from the glyph cache and the same sample width and sample height? I would argue maybe not, right? Like, these things are like, there's a chance that this could be wrong. And so maybe what we should do is we should maybe store the sample width, height, and the character map into something that we can pull in from our benchmarking script. That way we can like recreate this network with like exactly the same inputs. Seems reasonable to me. You could argue, especially because this sample width and height, I'm sure that we're going to be fiddling with those, right? These are essentially, when we look at this guy, the sample width and height are like, how many pixels from the thing on the left correspond to one character on the right? And almost certainly we're going to be fiddling with that. So I think probably getting this out of the way now and just writing that stuff down makes a lot of sense. So what do we actually care about here? We have the sample width, which you put a colon, sample width. You have the sample height. Sample height. We have like the character map, which we're going to have to generate. So for now, we'll do this. And then, what else? Is there anything else? I guess no, I think that's probably it. Sample width, sample height, character map. Sure. So where does our character map come from? This comes from like the sampler. No, the renderer car codes. Let's see. When we generate this guy, we run through all of the possible options and we render it, and we should just push back which character code is sane. But we don't do that, which is kind of odd. What do we do? When we create a cache of our glyphs to run on the GPU, we use this like image sampler, glyph cache, generate glyph cache. Generate glyph cache sounds right. Generate glyph cache, and we look at each character in the glyph cache already. What the fuck? Glyph renderer glyph cache. Oh, okay. I see. So when we render a character, there's two glyph caches here, which is kind of confusing. One of them is like, if we draw like the letter X, one of them boxes the character like this, perfectly, and one of them like figures out where he would be in some like uniform space. So in like the first level of cache, which we shouldn't have, honestly, we should probably delete it eventually. But we render this guy, and he also has some metadata like offset and like probably just the offset actually. Offsets of like left and right side essentially. So we generate this cache first, then we generate this one. And so this code is turning this cache into this cache, and he is iterating over all of the characters he's rendered, which seems reasonable. I don't know if like dictionary iteration in Python is like fixed order. So that's kind of scary. We might actually want to make sure that this is like index based when we pull it back. What do we do in our visualizer? We say that the label is just... Oh yeah, we iterate and we assume it's going to be the same, which it seems like is maybe wrong. Maybe wrong, but also, fuck it. If it works right now, it works right now. And so we'll maybe just do that. We'll throw a fix me on there that I'm not really positive about, but that's fine. Okay, so what we were doing, we were writing down all of the characters and their appropriate indexes. So for now, we will say, fix me, unsure if dictionary iter order is well defined. Dictionary. I put 2 T's. Iter is underlined, but that's a real word to me. We can say the car map is equal to, what do we do in our visualize script? We can just do the same thing. This. All right. So now we can save our car character map here. And we can just dump this out somewhere. JSON dot dump model params to a file. So with open model params JSON as F. Nope. We have to say that it's writable as F. Then we write this to F. Boom. We import JSON. Oh my god. Not this again. Oh, this like fucking indexer gets like stuck thinking that I'm like in some sort of file, and it just like fucking just pops this thing open and like hides half my screen. Can I? Oh god damn it, that's so annoying. But I think it's good. Can I turn that off? Config nvim init. That's broken. That great. More broken shit. And I think it's nvim comp cmp nvim comp nvim. Ugh, I don't know how to turn it off. I don't really want to figure it out right now. What a pain in my ass. It's okay. It's okay. We'll live. We'll live. We'll learn. Well, we won't learn. We'll live. We'll ignore problems. And we'll just get more and more progressively frustrated. And at some point, the frustration level will pass the threshold where we actually have to fix it. But we're not quite there yet. Almost there, but not quite. Okay. So we were in the training script, and we were going to write all this stuff out. We had to import JSON, which we've done. Jump to the string. And really, we should probably, like, not... Right now we're just dumping everything into the folder we're running the script from, and let's just not do that. So we can say output folder. Sure, yeah. Maybe output folder is not what we want to call it. Maybe we want to call it output. I swear I've done this before, but we must have just lost that code again, so that's fine. What am I looking for? Output. So he's required. Yeah, sure. And he's a string, so that's fine. And we'll just call this output here. And we'll convert this into a path. So I think it's from pathlib, import path, boom. Output is a path of output. And then you have like output, make their parents is fine. Parents is equal to true. Exist okay is not true. And that'll fail, and that's fine. It'll fail if the directory already exists, but that's probably what we want. I guess maybe unless the directory is empty. If the directory is empty, then it's fine to use it. So we can say if output exists and output is dir, output.iter convert this into a list, and we'll just assert if the length of this list is not equal to 0, raise a runtime error that says output directory is not empty. Otherwise, we try to make it. So we're kind of missing this case where the output is not a directory if it's like a file, but we'll just try to make the directory then, and it'll like fuck up because it'll go like, oh, what the, you're not a directory. And so we can maybe try here and accept runtime error, and then just print. Is there like a way to chain exceptions in Python? I think there is. Python exception chaining. Like I want to see like this is caused by this, which I think is raise. No, except as from raise this from that. Yeah. That's what I'm looking for. So we can accept an error E and say raise runtime error. I see you're on Nix.os. Is your Nix.files anywhere on GitHub? No, because I worry that there could accidentally be like keys and stuff leaked in there, right? I would hate to see like my S3 API keys like get onto the internet. Like obviously, like I don't intentionally commit those to my config repo, but like, you know, there's always a chance. So I just store it in my like local backed up Git repos instead. Failed to create output dir from E. All right. Sure. That seems reasonable. And then everywhere where we actually like write something out, we need to prepend like output dir like this. Is that what it's called? No, it's just called output. Dude, this fucking pop-up. I'm gonna. Dude, it's taking like the whole fucking screen. Okay. And okay, let's nvim comp. I'm pretty sure is the plugin that's causing this. Setup. So here I'm supposed to call require CMP. So surely, if I go into my config nvim in Lua and I look for Jesus Christ comp and I just say no. Get out of here. How do you comment in Lua? This. And, I think it's... That should be it. Let's hope that, like, my config still works. So we can go back to train. Py. It sucks to lose all autocomplete, though, which it also provides. Ugh. Okay, so it's like fixed, but like only kind of fixed. Like, is the pain worth it? Is it worth it? Is there a way to turn off the function declaration thing? Oh god. Oh, it's so well. Let's like. Is that even the plugin that's causing this? It must be, right? Local share nvim site packages plugins. Start. Yeah, I don't see anything else that's more likely to be it. Comp nvim lsp. Isn't this fun? We were trying to do something sane, like just write some code. And instead we're doing this. Okay, well, fuck it. We'll just leave it off. I think that we can code without autocomplete for one day. Right? Surely we can code without autocomplete. Hopefully we're not too lost. Okay, so we have an output. And what we're trying to do, we have an output directory. We're trying to put that thing everywhere. So when we render the image, we are going to render it to Output image. This goes to this format editor, so we just have to do output slash this. Whoa, 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 whoa. It's something else. It's something else. What do I have? Okay, it's... What else do I have in here? What's this? Don't think it's this. LSP signature. It is LSP signature. Aha! Which is what you said. I have a plugin called LSP signature, so I just didn't read all through my... Okay, that's great, because that means I can turn... We can turn our autocomplete back on. Thank God. Okay. So, setup. I just have to disable that part. Oh, thank God. Config, nvim, init. And we will look for LSP signature. We will disable this, and we will re-enable nvim comp, which is actually very helpful. Okay, and LSP sig. That's the only use of it, so it should be just... I think we should be just good now. So do we have, like, autocomplete? No. Did I restart? Oh, I didn't save this, that's why. File exists. Why? Of course it exists. I just opened it. Okay. Weird. So do we have, like... Okay, we have autocomplete, and... Okay, much better. Much, much better. Okay, we're living. We're living the dream now, guys. We have autocomplete, and that pop-up is gone. Okay, so here, we need to pass output here for now, and this also has to go to output. Alright. Alright. So can we now run our training script again? And it's going to say, hey, you need an output directory. Yep. And we can say output to temp, please. And he doesn't like that I'm trying to... Output is not supported for tensor and string. What the fuck? Oh, fuck. Output I'm also using as a name for the output of the network. That's so funny. Net output. I guess calling it output is not a very good name. So maybe we'll say the output is going to be output dir. We'll still call it output on the command line, because I think that's reasonable, and then everywhere else here we can just call it output dir. Okay, that's still output. This is output dir now. This is output dir. Maybe that'll do it. Unexpected keyword argument output. It's not metavar. It's there's an argument to this that says like what's the name of the thing gonna be? Dest maybe? Yeah, that looks like it's doing it. Okay. So now, are we writing into a file, a directory called temp? We sure are. Our state ticks are going there. Our images are not. Our images still being written here, modified. Just now, yeah, our images aren't going into that directory, which I thought they should be. What did I fuck up here? I just didn't type output here. And really, we should call this output dir. Wonderful. Wonderful. Cool. And our parameters look sane. Sample width, sample height, character map. Cool. All right. All of that so that we could run our benchmark script. So we now need not just the weights, but like the model definition. Model params, we'll call them. And I guess let's follow that convention that we just used. We're going to say model params. It's actually going to go to model params path, because that will avoid confusion. Because when we load them, we're going to call them model params, but that's different than the path they're from. Weights path. Device is still fine. Image path. I guess it's kind of weird that we write image path, but not model params path, so I think we'll just do the same thing here. Dest equal to image path. Get image path, model params path, weights path, and device. Okay. So now we need to load the network as well as the sampler probably. So we'll go back to our train script and see what do we do here when we start up. We create a glyph renderer. We determine our sample width and height, which will extract from the model params. So we'll say with open model params path. And this is, I guess it automatically sets read mode, I think, as F. We'll JSON load F. And we'll say that the model params are this, which means we need to import JSON. Are you finished with the torture, i.e. web dev stuff? Temporarily, I guess. I think that there's a good chance that we're going to find out that when we are training networks back to back, we might want some sort of way to visualize like the difference between different networks, especially like as they're training. So we might get back into web dev land a little bit there. But for now, the visualizer is looking pretty good, so no more work to do there for now. Let's just copy paste all of these imports and then delete the ones that it doesn't like. Later, model params not accessed, so we can say sample width now is model params sample width. And I guess you could write better code that like does some checking, right? You could call get and say like, you know, none, and then you could say like if sample width is none, you could then say like raise a runtime error with a nice error message. But I'm not going to do that because I'm a lazy fuck, you know? And the user of this is me, and I'm going to be able to figure it out. So I'll get mad at my past self in the future. My current self in the future? I guess in the future it will be my past self. Yeah, I'll get mad at my past self in the future when it doesn't work right. But future Mick is, he's resourceful. He'll figure it out. Okay, so we have our sample width, we have our sample height. Where were we? We're looking at what we do in our main function to get going. We have our sample width, sample height. We create our image sampler. That's still going to need to get done. Which is like our data loader, which creates labels. That's fine. He also does some stuff like conversion into tensor. Future me, what the fuck is this? Yeah, definitely. Luckily, he can't hurt me, though, you know? Future me has no ability to hurt past me, and so really it's like I'm only punching down from here. Okay, let's make a new script for just this, like, network. Definition, so that we can import it from multiple places. Sure, that was straightforward, which means that we can go from lib network, import network. Which means that here we also do the same thing, from lib network, import network. And now our network definition is no longer just raw here. Okay. And I guess when we want to run it, all we have to do is do this same thing that we did over here, where we say render the full image. I guess this is probably our benchmark here, where we extract the width, height, we extract samples of sample width and sample height from our image. We run the network on those samples. Then we iterate and stick those into an output array. Sure. And I guess that just means that this should also be in some helper script somewhere. Probably. For now, though, I am going to copy paste it because I don't want to think about where that should belong. I'll put a little fix me on him and I'll say, fix me duplicated with train script. Eventually there'll be a sensible place for that to live, but it doesn't exist right now, so I don't want to deal with it. And then we have our character IDs, and we grab them from the glyph cache, which is probably kind of wrong. I guess we kind of want to grab them from our character lookup. So here we're going to take in the image. We're not going to take in the glyph cache anymore because we don't need it. We're going to take in sample width and sample height. That seems reasonable. We still need to extract samples of that size. We don't have like an iteration here because we're not like training with iterations. We're just rendering. And output directory, we're not going to write the image anywhere probably. I think we're just trying to benchmark it. I guess we do want to write it out though to make sure that it's right. So maybe we'll call this like output file. Yeah, we'll just write the image directly. And the network. Okay, sure. And maybe output file should be the last thing, just because it's like conventionally it makes sense to have the output be last. Inputs then outputs, not inputs then one output then inputs again. So this extraction still makes sense. Still calculating the predictions makes sense. Figuring out the samples for the image, iterating. Except now our num y samples aren't going to be from the glyph cache shape. They're going to be from the. Oh, they are. We are still going to use the glyph cache in order to render the characters. That's kind of interesting. That's kind of interesting for sure. I see. So we actually have to generate our glyph cache from the character codes in the that we like wrote down. Which I don't know if we really like support right now. Because our image sampler just uses the glyph cache like or the glyph renderer directly. But we could just generate our glyph cache ourselves. So what does he do? He enumerates the glyph cache keys or the glyph renderer keys. And so we want it to iterate what we give it instead, which seems reasonable. Let's say that for now, we'll have an optional parameter. This probably won't be how it ends up looking forever, but for now we'll have a optional lookup, which is character codes is equal to a none initially. And we'll say if car codes is none, our tensor will look like this. He will use the length of the glyph cache as his output, as well as he will make his iterator will be based off this. Otherwise, though, our thing will be of the shape length of car codes, and our iter will now be enumerating car codes. And then here we say for idxchar and iter. And I think everything else just works. Probably. Sure. Yeah, okay. So when we run our benchmark, we have to gonna generate our glyph cache. So we'll say generate glyph cache. And what does he need? He needs the glyph renderer, and the car codes is equal to model params car map, I think we called it. And device is equal to device. All right. So now we have our glyph cache is equal to this, and then we just run the network. So render full image. The image is sampler image. Glyph cache is our glyph cache, not the one from the sampler. Sure. Sample width, sample height, network, and our output file. And so I guess we'll just write this down as output file for now, which means that we need to get the output file. Output file. Test output file. Or we'll call this what? This is like a rendered image or something. Maybe just call it output. Output path. And then here we take in an output path. And we also have to load the weights. So what was the torch thing for that? Saving loading models, load state dict, easy. So this comes from the weights path. And this just goes to output path. That might run. There's like a, let's say, 40% chance that when I run the script, it will succeed. Actually, there's a 0% chance because I called it output dir here. So here we just need to save to the output file instead. And I like this being output path better than file. Boom. All right. I'm at 40%. Let's see. So we need to pass in the image is sample pung, model params is from temporary output model params. Our weights are going to come from whatever like the biggest number in our current working directory is from when we trained at the beginning of stream, which looks like it's like 37,000 to 1, 38. Oh, 40,000's up there. Look at that. Okay. And what else do we need? We needed the output, which we're going to just call like test.png, which hopefully doesn't exist. I didn't actually check. And let's do this on CPU. Does that run? Is that everything? Size mismatch. Fuck. Oh, interesting. So copying a param with shape 1526 to 228 from the checkpoint. The shape in the current model is 3 to 228. So 3 is the number of characters. So we fucked up. We were supposed to, when we create our image sampler or our network, this doesn't come from the glyph cache anymore. This comes from the model parameters. Yeah. So this comes from model params car map, and this is the length of that guy. Like this. I think that's the right amount of brackets and shit. Key error 1525. Oh, oops. Because I just wrote, I don't know what the fuck I was thinking. Obviously, I'm not doing that. I'm just getting the length of the car map and using that as the output. Okay, cool. So size mismatch. 1525 is the length of the character map. What the fuck? Why am I off by 1? Why am I off by 1? What the fuck? Car X. Oh. There's definitely there's a bug in there for sure, somewhere. That's interesting. So let's run train again. So what I'm seeing is that I had initially filtered. So there's a fucking string in the character map. We're supposed to be mapping from character codes to glyph, rendered glyph. But there's a character in there. Probably because we render an @ symbol here to determine the character width. So if we do ord like this to turn the character into a number, probably we're going to end up not having that, and then it'll be fine. So let's train. Let's, fuck. No, stir object cannot be interpreted as an integer. So this is at line 81. Here. So which key, can we print the keys maybe? What's going on here? What's going on here? Why the fuck is CUDA in there? What the hell? That's very odd. Somewhere we're trying to render the device. That's very strange. Render car. Where is that coming from? I don't see it anywhere, really. Glyph renderer, render car. Am I enumerating the device here instead of the char codes? Generate. Oh, yeah, I am. It's because in the train script, here, we're passing in the device. We should be writing device equals device here. And that should fix it. There we go. There we go. That looks more reasonable. So we actually, unfortunately, do have to train for a little bit now because we've just altered the outputs a little bit. So we're gonna have to let them sit for a second. But we can at least monitor to see when it starts to look like halfway decent. We'll stop it because we don't need to get like perfect. We just need to get like okay, and that looks okay, right? In fact, it doesn't even really matter. We just need to we just want to make sure that like it's sane so that we can make sure that we're running the right thing. But I think we're good now. So our weights can now come from temp/900168. And I think the rest should just work. Perfect. Okay. So we rendered our image on the CPU, and we saved it to test PNG. Okay, so that matches with the network trained, so that's good. We have a way to run the network now, which is sick. And this is like the shittiest network of all time, which is fine, but we can now time how long that takes. So we can say import time, I guess. And we could say start is equal to time monotonic. End is also equal to time monotonic. And we just say print rendered full image in am I high? In end minus start. Jesus. I guess maybe we want to do it as a format string like this. End minus start second. So now we run the benchmark. Oops, that was a train. We wanted to run the benchmark. What the fuck? Oh, it was this. This was the benchmark string that worked. Sorry. No such file or directory. Oh my god. I fucking nuked the training directory. Fuck. That's annoying. I have to be careful about that. In fact, the whole reason of that output thing was to avoid that. And we're hitting this. We hit this yesterday where like occasionally my GPU just stops training correctly. I think I saw last night after stream that if I just reinitialize my environment, this stopped happening. Let's double check. Maybe we're fucked. Maybe we can't train, and maybe that just like ruins the stream. Yeah, that's so weird. I don't know, like my GPU gets into like some state where it stops like training correctly. I don't know if it's like the GPU. It's something about like it trying to compile something. Ugh. Can we train on CPU? How fucking slow is that? Are you running WSL2? No, I'm on Linux directly. Oh, training on CPU is so slow. Oh, I wish I hadn't deleted those files. That's so frustrating. Dude, that was one iteration. That one iteration took forever. Oh, but that was probably label generation was like taking a long time. Maybe let's print out how, let's at least like see. Let's just print out every iteration just to see how fast we're going, because god damn it. This is what I get for having an AMD GPU. That's what I get. I should have done better. All right, so label generation is taking like a million years. That's not awful. We could maybe, let's just like write it out every 200 or something. And probably after 200 iterations, we'll get something that's like not absolute shit. Fuck. That's so frustrating though. I don't want to have to train on CPU. It's maybe something like if a training process like gets killed unfairly or something, then the GPU gets stuck in a bad state. I don't know. All right, we'll train a couple hundred iterations on the CPU, and at least we'll have something to look at. That's fucking annoying. PS AUX grep Python. Maybe, like, is there any guy that's holding onto the GPU that shouldn't be? Doesn't look like it. TBH, my NVIDIA GPU is giving me issues with Leyland, wishing I had AMD GPU instead. I would say that, like, I've never had problems. Well, that's not true. I've had less problems on my AMD graphics card, like, gaming, for sure, and, like, doing normal stuff. But, like, at work, at the last place I worked, I had, like, an NVIDIA GPU and used it for CUDA, and that where it was, like, perfect. It worked great. Well, there were, like, still driver issues, but, like, way less so, like, the CUDA compatibility layer for AMD cards is, like, pretty fresh in PyTorch land. And so there's just, like, a lot of stuff that's, like, pretty hairy there. Last time I worked with this, I, like, used, like, this, like, Docker image from AMD that worked a lot better. But then, like, trying to pipe through some of the, like, Docker... If you try to do, like, anything outside of the Docker container, it starts to become, like, a giant pain in the ass. So maybe for this project, working in Docker might make sense because it might, like, clean up some of the, like, issues with the AMD card. But it sucks, like, the last project I was trying to work on locally was I was trying to work on, like, a video player that automatically tagged interesting sections of, like, video game highlights. Right, like, when do I kill someone in a video game? I want that to, like, show up somewhere. And so, like, playing that, like, trying to integrate that from within the Docker container just made me, like, give up on the project. I was like, this is so shit. It's so not fun dealing with that. So for this project, though, it'll probably be fine. Probably. Anyways, looks like we have some output. And I should just rename this folder from TMP so I don't accidentally delete it again. And it doesn't look great, but it looks good enough for us to benchmark. So let's kill the training process. Here we'll rename this to CPU trained. And we'll run our benchmark again. And this is no longer coming from CPU temp, it's coming from CPU trained. The weights are also coming from CPU trained, and we are at 1401. Output testing device CPU. Okay, so that took 170 milliseconds to actually generate the whole image. And that's like, that is what we had trained, even if it's shit. And then we wanted to compare that with, like, label generation, right? So label generation is going to come from, if we run sampler.get samples. What is actually, let's do it a little bit more explicitly. So get samples and labels for image. Okay, this seems reasonable. Actually, yeah, we'll just call get samples, fuck it. And we'll say start is equal to time monotonic, end is equal to time monotonic, and we'll say print label generation in this many seconds, and minus start. Okay. This has to close this. Okay, let's run the benchmark again, and we can see. Give it a sec. Give it a sec. Give it like 50 secs. Give it like 100 secs. Jesus Christ. So this is why the AI is the way, because this label generation is taking like so goddamn long. Holy, it's still going. Label generation in 30 seconds. Holy shit. So that's like what order of magnitude speed up is that? Like, or like how many X? That's 10, 100, like almost 200X speed up. That's crazy. So that gives like confidence that like the concept is strong. Now, obviously our label generation might be shit, right? Like we haven't like tried to optimize that at all, so there's probably a lot we could do there. But like just taking like the stupid thing we did with the first thing we tried for label generation, the first thing we tried for network generation, we're at like massive gains, which is pretty fucking sick. And I wanted to see if generating like one hidden layer resulted in like similar performance without with like also a massive speed up, right? Because we can imagine, we kind of said this at the start of stream, but right now we're kind of doing like pixel go to all characters, right? Boom, 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 boom. So you have like number of pixels times number of characters is approximately how many like computations you're doing. But if you did like pixel go to like intermediate thing, go to characters, if you have like 30 intermediate things or something, you have like pixels, you have characters. Now you have pixel times 30 plus character times 30, which is like theoretically much faster. So I did want to see what that would look like. So we can go to our network, which is over here somewhere. And let's just add in a second layer here. Which we'll say it goes like 30, 30. I'm picking like 30 because like I'm kind of thinking about how many things would you need to check like about pixels relative to other pixels to get this right. 30 seems reasonable. Who knows if it's reasonable? I'm just like picking it. I think like 5 would be like too low. 100 would be like maybe too many. 30 seems like, I don't know, fuck it. Reasonable. And then let's give it like the ability to do like a little rel u in between. So we'll do, we run the first layer. We do import torch.nn functional as f. Then we do a x is at rel u on x. And if you want a little bit of context on why we're doing this, we did a while back, maybe like a couple weeks ago, maybe last week, we did a stream where we basically tried to like intuit about really shitty neural networks. And basically like the rel u allows you to like stitch together linear functions in a way that like just multiplying values together doesn't. So anyways, that's why we're doing that. And then we say, then we run it through the second linear layer. And then return x. And we probably don't need to do any like rel u at the end of the second linear network or the second linear layer, probably because it just decided like the output of this guy is supposed to be like probability distribution of each character, right? So like big number for right character, small number for wrong character. And so like doing some sort of like activation on that, we're saying like it's good if it's above some number. It's like, why, right? Just make a bigger number, man, right? Just try to make the number as big as possible for correct. So I think that we don't need to do an activation there. We'll see. We'll see if this is at all reasonable at all. So now we can say that we are going to train, and we are going to output this to 30 or 1 layer. I'm trying to not start with a number because I feel like that breaks things sometimes. Let's say that we're trying to do output 30 hidden for a 30 node hidden layer. And let's get optimistic and then get mad when it doesn't work. We're going to try training on CUDA again, but we know that it's going to fail because it failed every time before. Fuck! Now we get frustrated. I fucking called it. It'd be interesting to know if you can like reset the state of this. I don't understand why it's like it's ephemeral. Why does this only happen sometimes? Hold on. I had a trick somewhere. Hold on. I think I've seen this exact error before when I was working on something else before. Let me just go into my other account and see if I can find hold on. There's something somewhere. In my Nix shell, maybe? I'm doing this off screen because it's not in my like super secret streamer account, so I don't want to leak any like valuable information. Not that I would have any, but just in case. Hold on. One sec. Here it is. This is what I'm looking for. Hold on. I don't know what the fuck this does. But I did have this written down somewhere. And I had written down that basically there's like some problem where it's trying to do like a convolution and it's trying to like compile something to run on the CPU and it's failing to find lib, like the standard library headers that it needs to do so. And I did like this like dive into whatever the fuck MIOpen is at some point. And I basically found that you can like set some environment variables to force it to take like a different path that just like happens to not have the same problem. But I don't know like what the effects of these guys are. So it like might be like shit. But let's just try it because I don't want to deal with where the fuck did my command go? Train. Was I in this window? I was. Here we go. So source m.sh and let's just try after doing that to see if it works. Output directory not empty, fine. So we'll remove it and we will train again. Oh, we're so back, baby. Who knows what those do? Or why they're debug flags or why, but mwah, we're back, baby. We're back. And so let's see if like the outputs of this are like reasonable at all. We are rendering. Oh, that's nice. Okay. Who knew it pays off to fix problems? Okay. So this is with 30 hidden, or one extra layer with 30 nodes. And it's got come to the answer like one, maybe quicker, right? This is looking like arguably way better at 3,200 iter than we were at like 40,000 on the other one. Maybe. I don't really remember. So maybe I'm just making shit up because I want like confirmation bias. But that's looking pretty good. And let's run the benchmark again. But instead of running on the CPU train, we're going to run this on what do we call it? I already forgot. Output 30 hidden and model params. Weights. Output 30 hidden. And we want to just like look at some recent state tick, doesn't really matter. Output assess something, device CPU. And let's comment out the like label generation part because we know that that's going to be like the same painful a billion years. So we'll just comment that out. Doesn't fucking matter. And we're at 0.19 seconds. And what were we at before? I think it was faster before actually with the older network. Before it was at, was it 0.18? Did we lose, or we can, I guess we just undo these changes and run it again with the CPU one. Oops. So what was it? It was benchmark, but before we were running with the old model params. 0.17. So interesting. I actually expected that to get much faster. But it's not. So I'm kind of surprised there. But that's interesting. So theoretically, what would happen if we did this with like, 10 hidden nodes? Or maybe like one even. Like let's just get like crazy just like for like speed purposes just to see. So let's do a train here with output 1 hidden. Just give it a sec to like bang out a couple iterations. So here we can see almost certainly this will become shitty, right? Certainly one piece of information about all of the pixels is not enough to get the answer right. But I'm actually kind of curious now because like that's like kind of, yeah, absolute fucking garbage, obviously. But I'm curious how fast that would be if it was good enough, right? If it was good enough, how good would we be? So we have the model params is from output 1 hidden from model params, and then we have I forget all the inputs already. Fuck. We also need the weights, right? Obviously, we need weights from output 1 hidden, and we just like it doesn't fucking matter because they're all shit. But in fact, we don't even really need to load weights because it's so bad we don't even really care. So that's interesting, actually. The like upper bound here, or the lower bound on how fast we can get, is actually not that much faster. So it's possible that the speed or like the slowdown is maybe not actually coming from running the neural net. And so we should actually look at how much of this cost is from writing out to the image and how much of this is coming from the actual network run. Because that's obviously the part that's important here. So start is equal to time monotonic, end is equal to time monotonic. And let's say print running neural net took this long. And we'll do this again with, oh, he doesn't like that I misspelled format, which is reasonable, right? But I mean, maybe just like grow up a little and like live with it. Yeah, okay, so here with one hidden node, we're talking like 1 millisecond. So let's go back to the 30. Let's go back to 30 here. And benchmark it again, baby. But we wanted the output 30 hidden. Okay. So 14 milliseconds with 30 hidden layers is not that bad. Not 30 hidden layers. What am I talking about? 30 nodes in a single hidden layer. Not that bad. And on this single image, pretty decent, right? Like the results were like pretty good pretty quickly. And so what might be interesting now is to try to like update or upgrade our thing. Well, actually, let's just try running on another image. We don't even have to like, we don't have to actually train on another image yet. Let's just see if we transfer at all with something so naive. So the picture we have right now came from DuckDuckGoing the word picture. Let's just try a different one. All right, so we will save the image to our downloads. And let's just, first let's see what the best, like, what is like the best world for that look like? If we were to get the answer perfect, we would look at downloads. What was it called? Sunset? No, it was called something.jpeg. Pixels photo, maybe? That looks like it might have been it. Oh shit, maybe it's like a big picture. That looks like it's struggling. Maybe we have to resize it down a little bit. How big is this? Oh shit, that's a massive image. Holy shit. Okay. Open with color paint, and let's just kind of resize and scale it down to 1080p, baby. All right, save. And we'll say sample to, let's save it as a PNG because we like those better. Sample to Pung. Real question, can it do anime? I mean, I'm sure one day it will, but I will never try it. Someone else in the world might, but I'll never find out. Okay, so if we look at our visualizations, this is our image. This is what we expect to see. Wow, that looks fucking good, by the way. Let's like look at our different, so if we were to just look at pixel brightness, shit. Look at like a raw diff over contrasting. Whoa, look at that. You get like little highlights on here. So let's see if our what we run looks anything like that. So let's run the benchmark. And this is gonna come from now downloads sample to PNG. Let's just see. Did it learn anything? Did it learn anything? Well, it learned something. Did it learn anything that transfers? Work, image ascii, and we save this as test.png. You know, that's not awful. That's actually shockingly good, given that we've only ever shown it one image. That's not bad. Okay, so like the hypothesis when we started this whole thing was that the problem is dead fucking simple, right? Like dead fucking simple. And this is kind of like indicating that that's true, right? Man, that's fucking sick. So obviously, like, there's some things in like the generated labels that it gets a little that are look a little better, to like compared to real, right? Like it's kind of like the grays are a little grayer, and like the stems and the trees, I think that they look a little nicer. The reflections a little better, but overall, that's pretty good. And so I think probably we like the question is, what do we do with our neural net now, right? There's okay, how to say this? We're looking for the fastest we can fucking go with like a minute with some lower bound on like quality, right? So it'd be kind of interesting to just take this like shitty neural net currently and run it and see what happens. Does your neural network take neighboring characters into account? Oh yeah, okay. So there's like some like problems right now for sure. First of all, we don't even like this. We should be clear that this is not an accurate representation of how it would come out when you wrote it with characters, right? Because what we're doing right now is we're stamping each image into like a fixed, basically, stamping each character into like a fixed image size, which is not how font rendering actually works. But it's like maybe close enough to like proof of concept. And then so this is like those things copy pasted into here, which like is, we can actually see somewhere. I think somewhere I try printing it out and we'll see if it's like related at all. Can we maybe? Actually, it's not that bad. What we get out when we actually render to the terminal is like close but not perfect, like not as good. But this is also like a different font, so it's not like a fair comparison. And so you're asking, does it take into account neighboring pixels? And the answer to that is also no. We basically just take a stamp that's like the size of this glyph, shove it into the network, and then say, give us the character, baby. And I do think that probably eventually we will want to look at expanding the area, as well as I think that if we wanted to handle non-monospace fonts, there's something interesting there about like you're going to have to like give it an area that's like too big, and it's going to have to kind of learn which characters would fill up which areas of that image. And then we would have to do like a loss on like the whole image instead of the actual thing. But that's a future stream problem. How hard would it be to contain color information? I think I have to think about this a little bit, but I suspect maybe not trivial, right? Because what we're doing right now is we're looking at like each character. We're assuming that it's going to be rendered black on white, or sorry, white on black, right? Which is like not really like a valid assumption, but it's like a good enough assumption for now. And you can imagine that like if you were allowed to change the foreground and background colors of the character, what does like that mean, right? Because now all of a sudden, like something like this is probably going to end up being like a good answer for almost every single fucking character spot, right? Because all you have to do now is just say like, okay, how many, like if we have two tone, like you could just pick two tones that are very close to each other and then dither between them to get like the difference or something. Like there's probably something about that makes this problem much harder. And so in that world, I don't really know if picking the shape first makes sense, right? In that world, it probably makes more sense. Like right now we're like generating labels and saying, here is the correct character. And we've like pre-calculated the correct character. And I would wonder if in that case, it would make more sense to not do that. In that case, we might just want to render the image with what the network generates and then calculate how bad that is based off some metric and just say, get closer, right? Because like the color and the shape are then like intertwined. But I could be wrong there. I need to think about that a little harder because I would like to think that there's a world where we could pick the shape first, then pick the colors, because that's like a simpler problem for like to architect. And then also, then you can train one neural network that would predict both shapes that would work in like two contexts, right? There's like one context where you're trying to render into a terminal and you have all like color codes available to you. But what if you're like trying to like take a picture of a meme and then paste it in like, oh my God, I almost said Facebook chat. How fucking old am I? Jesus. Into a chat with your friends. where you like can just like paste a monospace thing. Or maybe even if we support non-monospace in the future. But in that case, you only have black on white. And so then it might not make sense to encode color in there. So you might need two neural networks. I don't know. I have to think about it. But I think for now, let's see. What do we want to do? Let's upgrade our data loader maybe and try to train on a few more images. Okay, well there's two paths we could go down. We could try going down a road where we try to train on more data and see how well we can get the network to like generalize, right? Theoretically, if this image was in our training set, it would do better on this image, right? Obviously. But the other thing that we could look at now is trying to like reduce the network size and compare them with each other, which means like writing down the loss and stuff. Yeah, it'd be fun to experiment with color in the future. I definitely will experiment with color in the future. We're definitely going to get there. It's just, well, I shouldn't say definitely because there's always the chance that I just get bored and do something else. But I likely will get there. I want to, at the very least. Okay, so do I want to start with trying to upgrade data or try to like get the network smaller? I think let's go with upgrading the data loader. I think I want to do that first. So we're going to say we did this, and then at some point we kind of went on like tangent talking about stuff. Don't remember. And I have to write this down because later I'm going to be making YouTube timestamps based off this, so I need to like write it down. And then at around 2140, we're going to try upgrading our data loaders. Oh wait, actually, no, I don't want to do that yet because I wanted to look at speed. I forgot. Okay, so we're at 14 milliseconds, and I actually did want to see like, can we push it a little farther? I did want to see that. Like if we tried like 15, like just hand wavy, like fuck. I wanted to see if we trained on like with less, we can approach that like really, really fast speed and maybe still get like an okay quality. So I did want to see like how much does it actually need for this one picture. Oh, and since we're training on the GPU again, we can stop fucking logging every 200 iterations. We can actually go back to like 1,000, which is like way more sane. I don't want to like fucking spam output. Directory's not empty. Fine. Fine. Okay, there we go. So now we are not spamming, and let's see, output 15. So the loss is still getting like pretty good, pretty quick, right? We're down to like 0.6, 0.4. I think that like we were seeing like 0.2, 0.1 or something, but like already that's pretty good. Look at that. So even with 15 nodes, that's easy peasy. And then let's maybe, let's give it, I want to give it like a couple thousand more just to see. Yeah, that's looking decent. And it doesn't look like it's capped out yet either, which is pretty cool. But I just wanted to run the benchmark with that and see. So benchmark on this. We'll use the same other sample just to see how well it transfers. And anywhere we see the word, the number 30, we're going to write 15 now. And we're going to run on the CPU because that's where like it's going to be slower and we can like get a better feel. Oh, except the state ticked is wrong. Fuck. The weights come from whatever the latest 9,000. Sure. Oh, unless we got into like, why is like the fucking, why is the autocomplete like so far over? Here we go. 11,000. And otherwise, I think we're good. So that's 11 milliseconds. And what were we at before? I actually already forgot. Running neural net. 14 down from 11. That's actually not that big of a change. Or sorry, 11 down from 14. So we might want to strike like a reasonable balance between like pushing it farther might give us like a heavy reduction in quality for a pretty low gain in time. Hand wavy. But, you know, let's just kind of leave it there for now. So then at some point, which I also don't remember when, we started looking at reducing number of nodes in hidden layer. All right. But I mean, 11 milliseconds is great, right? You could do that 3 times a frame at 30 frames per second, and you could still do it like over once a frame at 60 milliseconds or 60 frames per second. It would take up like the majority of your frame time though. But I mean, we're also talking about doing that on the CPU. If you do that on the GPU, it's probably like blazing fast, which isn't a fair comparison, but oh, that's pretty funny. Time probably actually went up because the transfer time from CPU to GPU probably is like more expensive than like actually running the network. That's pretty funny because it's such a simple network. Usually you get like the big increases because your GPU is so much fucking faster. But the networks are usually so big. You're usually doing like billions of computations, and now we're doing like what? Like, what's our sample width and height? Can we just look? Model. We're doing 12 times 19, or yeah. What's the math here? 12 times 19 for number of pixels times 15 plus 15 plus 15 times number of characters, which is like probably like 1500 plus 1500 again, so 16 times 1500. Yeah, okay. Which is what? 12 times 19 times 15 plus 15 plus 15 times 1500. 25,000 floating point computations, which is probably like cake for the CPU. It's probably not a big deal compared to like actual transfer of data. Like the actual data transfer might be just more than that. Oh no, the data transfer can't be more because we're only transferring the samples and the weights. So you basically have to like multiply that by 2 because all of your weights and all of your pixels have to go to the GPU. I don't know. The weights should already be on the GPU. I don't actually know why it's taking so long. It must just be that like the sample transfer is just expensive as fuck. Well, expensive as fuck relative to the cost of actually running. Oh, all right. Surprising to me, but interesting. Interesting. Okay. Let's look at integrating more data. So earlier I was trying to download some of like the Torch Vision datasets. I was looking at this. I was looking at, which one was it? Places? Something Places? I was looking at this one. I looked at a bunch, but I was looking for something that had like reasonably sized images as well as like large variety. I don't actually care about their labels, so like using a data set used for AI training is like maybe not important, but they're easy to get at. I was also looking at some of these ones that are like 32 by 32 pixel images, which are like kind of small, so I would like prefer to use bigger ones because I think that like probably the images should be like representative of like the types of things that we would end up converting. So you can imagine that these like 32 by 32 images, if you're taking samples of like 12 pixels, then you're almost getting like a full picture almost, right? You need like 3 characters to render the whole picture, which isn't really reasonable. Where like if you're looking at like a normal looking image, then your things are going to be different. Maybe you could argue that our neural network should support variable size of samples, or that we should like do some pre-processing in order to make everything kind of uniform size. But I don't like for now, since like we're at stupid stages, fucking dumb as bricks. It makes sense to just kind of make sure that all of our inputs are approximately the same size. So we just start with something reasonable. Anyways, I was looking at this and it's fucking huge. I started downloading it like an hour before stream started and only got like 50% done, and so gave up. And it sucks because the download is like a tarball instead of like individual pictures. So it's like all or nothing, I think. I actually don't know. Are tars like is all metadata at the front? Can you open a tar without whole file? Is that like legal? Actually, we can just try it, right? Because I probably still have it in here somewhere. I don't, because I was downloading it to the folder TMP and I deleted TMP. Ah! I should stop deleting stuff. Fuck. All right, so I don't have it. Even like the part I did get. So maybe it's like maybe we start like poking at a couple of other ones of these and see what we get. Eurosat. That sounds like satellite data. Probably not representative of things that we would actually do, right? If we're looking at like pictures of landscapes and stuff. Flowers might be Flickr. 8,000 images from Flickr. Those should probably be pretty representative. Oh, that looks kind of sick. Let's see, what else is in here? Pictures of cars, guys snow. This is actually probably about as ideal as it could get, assuming that this is like like the data set's not too big. Motorcycles. What else is in here? There's a lot of like labels, but oh, these are sick pictures. Yeah, okay, let's try this one. And presumably the 8K is talking about 8,000 pictures, would be my guess. Not 8K images, like 8,000 pixel large images. If they are, then we're gonna have to reduce them. But let's try downloading this and just see what it looks like. If this can be downloaded relatively quickly, then we'll use it. So I already did this. Like I want to try downloading this, and let's try. We'll say dataset. We'll say that we want to download Flickr 8K. Just to see. Missing parameter for and file. So what are like the parameters here? Root and file. And file. Path to annotation file. I guess we'll just call it dataset JSON. I don't know. The annotations are probably on JSON, right? And can I download these? Oh, this doesn't have like an automatically download. Oh, that sucks. Can I, like the other one had like an auto download, which was exactly like the only reason I was using it at all. All right, we'll look at a different one. Or can I like, is this like downloadable in some way? Is this just like a fucking HTML page where I have to like walk the links myself? I don't want to do that. All right, never mind. We'll try a different one. ImageNet's fucking huge if I remember correctly. LFW, looking for label in the wild. Fine. Faces. I don't think that's like maybe interesting, but maybe yeah, sure. 173 megabytes. That's not very big. Sure, fuck it. 11 minutes though, because I'm only downloading at 300k. God, so slow. I'll keep looking. Oh, looks like maybe it's accelerating. 500 kilobytes per second. We're fucking at light speed now. What else is there? Q minced. Those are numbers. Rendered to original character, optical character recognition. Boring. Cars. What's STL? Standard template library. This looks a lot by C410. In fact, it's inspired by C410. Is there images like reasonable sized? Oh, this is just all of them. Who knows? Who knows? It doesn't say. Oh, 96 by 96. That's a lot more reasonable. We'll keep this one in the. We'll keep this one in like the thoughts. 96 by 96. It's still pretty small. Is USPS mail? Is this a mail data set? Oh, text recognition. Boring. All right, whatever. Did our people faces download yet? Another minute. We have to waste another minute. What's an omniglot? Text again. MNST, I think that's text as well, if I remember correctly. Handwritten digits, yeah. Lots of digits. Why do people like digits so much? I guess character recognition is probably pretty big. You can like scan books and digitize them, and there's probably a lot of money in that. Probably. I guess it's like probably just recognizing writing in general is probably a pretty interesting task. That probably comes up a lot. Any thing that's trying to navigate the world certainly needs to read. Maybe not. Maybe. All right. I would have liked that Flickr dataset, but maybe the Flickr 30K one lets me download it. Where is the... Nope. They still expect me to download externally. All right. We're almost at the face one, which is actually a problem because I actually forget which one of these the face one was. Fuck, was it LFW people? Yeah, it was. Okay. Okay, so we'll try looking at a data loader of LFW people and see what that looks like. An idea for a future stream. Yeah, sure, why not? I'll take a look. Maelstrom. Learning distributed systems by writing your own. Workbench for learning. What is a workbench? But like this is just distributed database? Is that kind of what you're thinking about? Distributed systems are kind of fun. So we'll keep it in mind. I think that probably I have like some other ideas that I'll want to get to first, but we'll get there. What OS am I running? I'm running Nix OS. I always kind of flag this with I don't think that other people should run Nix OS unless they really want to. If you're looking, obviously, I think it's great for for reasons that I like, but I never want people to think like, oh, it's a. If you're like, should I use Ubuntu or Nix OS? Like, probably use Ubuntu. If you're like, if you like what it provides, which is like a, it lets you have like multiple versions of the same software installed, as well as like huge backup, like full backups of like each time you upgrade, you have like both versions of the OS still there. You have like your operating system is like tracked by a single config file or multiple if you want to split it up. But you can like track your whole operating system in like Git, which is pretty sick. I have mine set up as a Git repo that I have a branch for each computer I have. And so what's pretty sick is when I like start up a new PC, almost everything's like exactly the same. I just have to like change like a few variables. Yeah, it's pretty sick. Pretty sick. All right. Okay. Sure. So we have this data set that has pictures of people's faces, and we can try using this for training. 250 by 250 is like pretty reasonable. So let's maybe just take one of these guys and run him through our visualizer just to see if like a sample size of 12 is reasonable for these. And we can look at our visualizer, refresh. 12 seems too big, which is kind of unfortunate. But maybe it's okay. If we're just looking at like individual samples, then maybe like the variety in here is like enough. Yeah, that's probably fine, actually. Like feature size relative to like the number of pixels in the scene is like pretty reasonable, right? Like we were getting like, you know, if we were like at the edge of her lips, edge of her shirt, that's like approximately the size that I would expect. So sure, we'll try using this and see what happens. Which means that we need to figure out how to use these like torch vision data loaders. So we want to create an LFW people. And so can we just say like, let's open up our test script here. And we'll say, I want to try using this. Oh, fuck. Oh, fuck. I want to try using this with a T on it, torch vision. And let's see, what are the arguments here? The root is just at home streamer downloads and LFW. And if we try to print out the first item in the dataset, we can just see what it looks like. Permission denied, Python 3 test.py. Dataset not found or corrupted. What do you mean not found or corrupted? Does it want like the tarball? Where directly LFWPY exists. Oh my fucking god. So what I downloaded wasn't the right thing? So I didn't even like fucking... Oh! Okay, you know what? No, fuck it. We're just gonna write our own. I don't want to go through that data download again. So we're just gonna sample it manually. Fuck it. God. Okay, so my auto completion for like file paths is getting like really fucked up because there's like a million files that I don't ever want to edit. So probably what we should do is we'll make a directory called training output. And we'll just take all of our outputs and stick them in there. I don't want you. Let's delete all of this stuff that's like just raw sitting in this folder. I don't need any of this. And And this like output stuff I also don't need. So can we just like rm-r all of that? That's a dangerous command that I shouldn't just like randomly type, but you know, it is what it is. This goes in the training output as well. And I don't know what this like before and after is, so I'll just delete it because I don't care. And then we can go to my git info exclude and say remove every, like, ignore training output. Training output. And we say we're going to do it that way because that's like, there's like git ignore, which is like tracked by the project and like has like project ignore files. But like, I'm like, I don't want like to say that the project isn't allowed to have a training output there. Just I happen to put my files in a folder called training output, and that's like a choice of mine. So we use git info exclude instead. And now we're back in a reasonable state. Very sick. Okay, so in our image sampler, right now we have like our data comes from image sampler. And what we want to do now is instead we want to load images from those people. So we'll call this what? LFW, or I guess we'll just call it like nested images, nested dir image loader, right? Theoretically, like we're using this on the pictures of people's faces that we just downloaded, but we don't actually care that it's the people's faces. We just care that it is a bunch of pictures. And what are we gonna do? We're gonna come in and we're gonna ask for the sample width and sample height again, probably. We're gonna want the glyph renderer. Oh, what is this guy doing? He's doing a bunch of like setup where he takes the image, he resizes it. We don't really need the glyph renderer. We'll just take the glyph cache here instead and generate it externally. That seems reasonable. And why does he ever store, like, use these character width and height? It doesn't look like it. Okay, so let's just do that. We'll take in these guys. And so this is going to be an int. This is going to be an int. And this is going to be a tensor. And then what we're going to do, we're going to, we also have to take in, like, the image directory. Which I guess we'll take in as a string. Or, like, it could be a string, it could be a path. I guess we'll say we don't know. And we'll say image dir is a path of image dir. Just in case it's like a string or a path, then everything will get auto-converted into what we want. Which means that we need from pathlib import path. Then we're gonna like find all of the images in that dir. So we're gonna say image dir glob anything that is a PNG. Reasonable. And then we will just print this for now. Images is equal to this. And then we can go back into our like test script. And we can say from lib.imageSampler import nested dir image loader. Fuck it, sure, whatever. And then we'll just say nested dir image loader with home streamer downloads LFW. Looking for what? And we have a sample with, well, we don't really care. We're just gonna put a 12 by 12 in it for now. And we're not using the glyph class right now, so we're just gonna say torch.tensor with nothing in it because it doesn't fucking matter. Image loader is equal to this. We need to import torch. And can we print the image loader now? Or yeah, I guess that will do a print for us. So we can say Python. I actually want to say this is a user bin env python 3 so that I can run / instead of having to type Python every time. chmod plus x test.py test.py. We get nothing. So that glob didn't work. Is it because they're not PNGs? Is it because this folder's wrong? Star. JPEGs. They're JPEGs. Gross. That's okay for now. Okay, so there we go. We have all of our JPEGs available to us, and let's how many of them are there? 13,000. That's a lot of pictures. All right. So then let's say we have like the ability to get some samples. And what does that like entail? We're gonna load the image. So I guess we're gonna need like the concept of like epochs, probably, right? So the idea is that we want to run on all data in the data set before repeating, essentially, right? And then you can like say to yourself like, oh, I did this many images, hooray. So I think that what I saw the data loaders do there is they have like the ability to get the samples for a single image, and then they randomize the indexes into the thing so that you don't like train in the same order every time, and then iterate that way. Do I want to do that? Do I care right now? That sounds like extra complexity, maybe for no reason. Nah, it's fine. It's fine. Okay, so let's do it. So we'll say def get sample for I. And here we're gonna say image.open, which is certainly not the most efficient way to do this, but that's okay. We're gonna actually save these images as self images like this. Like this. So now we have a list of images, and then we can just say image open self images I. And then we can turn that into array. And I think the reason that we would do it this way is because we don't want to like keep all of the images in memory all the time, because it's just like not really reasonable. We should just open them and then save them after. Open them, like load them into memory as we need them. And so then we say what? We have images. This is an image. This is image to open that. What do we do with it? We get samples and labels for image. Okay. So I guess we have internally, we have sample width, which is width, like from the image, how many pixels will we look at once? But then there's this like upscaled image shit that we're doing here, where you have the sample width is, there's also this like glyph width, right? So we like render the image render each character, and it ends up like being like a certain size. And so we basically need to make sure that sample width has to equal glyph width for our comparisons to work. But it just doesn't, right? So what we end up doing is we do like sample comparison width, and then we like take our image, we upscale it so that it's this like the sample sizes match up. And then we run this like get samples and labels for an image. So hopefully this will just still work. And we just store the sample width and sample height. That seems reasonable. So like this, sample width, sample height. So here, instead of self.image, we're going to do image, which we should use abbreviated because we're doing that everywhere else. Mixing and matching full word image and abbreviated would just like absolutely like mind fuck me. I'd be so fucked. Then we need to resize it up so that the image is divided by the sample width times. Oh, I see. So we're doing this, gets us like the size of a sample. This tells us how many samples are in the image, and then we multiply that by the size of the glyph render. Yeah. That seems reasonable. So image.shape. Nope. We're gonna convert this into a torch tensor off rip. Yep. So we torch tensor, which has to be on the correct device. I guess we have to think about, you could do this on the CPU or the GPU, and I think I've seen that like Torch has their data loaders. They do a bunch of like preloading on the CPU so that they can like use all GPU memory for training, and then you just like max out your CPUs just preloading data so that hopefully you have enough when the GPU gets the next iteration. But I would bet that in our world we're probably like GPU or I would bet that our labeling process is probably the most expensive part, but that doesn't matter. Yeah, for now, we'll say that device is equal to self.device, then we can experiment. So we'll just kind of say at the end here, we take in a device, and its default is going to be CPU, but we can override it if we feel like it. Okay. So our glyph cache is going to be a tensor of number of characters, height by width. So our resize multiplier is going to be the glyph. Resize multiplier height is going to be the glyph cache shape 1 for height over our sample height. Yep, that seems reasonable. And the width is going to do the same. So it's going to be shape 2 over the sample width. And actually, I lied. We're not going to go straight to a tensor because we want to be able to call image resize. So we're going to say image for comparison. Comparison is equal to image resize to its current size, image dot size shape. What is like my, what does image open return? This returns a image, and can I see like this is a module image open returns. Where do I see like the class? Oh, just fucking look it up. PIL image width. Surely, like, size, of course, not shape, size. Which actually does just make more sense, but I want to act a little outraged. So I think the width, I think that PIL is width height, so we say resize size 0 times resize multiplier width, and then image dot size 1 times resize multiplier height. Okay. And sure, that seems reasonable. And then we get the samples for image, so we say self sample width, self sample height, torch tensor of image. Maybe we have to convert this to a numpy array first. I'm not sure, but we'll find out. And then torch tensor image for comparison. And the glyph cache. Everything else should just, that might just work. There's like a good chance that just works. So let's make a glyph cache, I guess. In our sample script. Which means that we need a glyph renderer somewhere. So we create our glyph renderer, use that to make a glyph cache. We'll just hardcode CP for now. This is renderer cool from lib.image to text import glyph renderer. Image to text? It feels like this glyph renderers are text to image. Seems like kind of a backwards name there, but whatever. We need the glyph cache, so this is generate glyph cache. We generate our glyph cache, and then we load the images. We pass in here, instead of an empty tensor, we pass in the glyph cache. And we just say, what happens if we say print image loader get sample? What do we get up? Is it sane? Who knows? Who knows? We'll find out. It's going to crash, certainly. Okay, so unknown resizing filter. So we fucked up something. In our other thing, when we resize, the resize is a 1 argument for the new shape or the new size. Test by. Float object cannot be interpreted as an integer. So do we just floor this? The resize multiplier. So what's happening here? We have like sample width. We're finding like a multiplier from sample or image width over sample width is equal to some integer. And so we just need that same integer for times. Okay, so this should be, oh God. Can we just like, so this is taking in a new absolute size in pixels. So I guess we should actually say that the number of samples that we support is an integer floor of the shape over the samples. Num samples on height, num samples on width is this. And then we just multiply these by the glyph size. Yeah. So this should just be num samples width times glyph cache shape 2. Oh, this should be the glyph cache. This should be image. Fuck. What am I doing? Num samples width is the image size 0 over sample width. Yeah. And the height is image size 1 over self sample height. We integer floor, then we multiply these by the glyph cache shape, which seems reasonable. Num samples height times self glyph cache 1 for height. I think. Shape 1. And I guess probably these are going to turn into floats. So maybe, or are they two integer multiplied together? Or should stay integer in Python, I think. It's the divide that upcasts into floats. A tensor object has no attribute sahib. Fine. I'll type it right. Like, wow, that was an atrocious typo. Okay, cannot infer the type of JPEG image file. I see. So probably we need to do a like NumPy and darray cast from this first, which is kind of silly, but whatever. No? How do I turn an image into a... What did I do before? NumPy array, not ndarray, obviously. Obviously. I should have known. Okay, so that gave us something. And it would be interesting to see what, like, the label is. So we can say print data labels is equal to this. And can we just like, what's like the quickest way to deal with this? I don't know. Fuck. I want to like visualize to make sure that this sample is like, that this is sane. But it should be, but there's a way to check easily. So we can say for I in len data, we take the data and we save it. So we say image from array data dot cpu dot numpy. We need to import PIL from PIL import image. And we can just save each picture at its index and then write down what character that is. And we can just check if it's like somewhat reasonable. We don't have to be too careful. So we say CPU numpy, then we save it. Save to what? I.png. And I think we also multiply this by 255 and cast it to a convert mode is equal to L. I think that we've done this a few times, so I'm pretty sure that was the pattern, but I don't quite remember. And then we just print out I and the label. Which means what? We have renderer. We need the car map. So we did that thing where we did chr I or C for C in renderer.glyphcache.keys. Something like that. So you can just say print IC. Car map. Labels. I. Something like that. We'll find out that it's fucking broken in a second. Alright. So cannot handle data with this type. 1, 1, 12. Oh, do we need to convert them into black and white images when we open them? We probably do. Yeah, like this. We want them to be black and white, but they're normal pictures, so they're a problem. Interesting. Still doesn't like that. So what are we, like, where is it going wrong? It's going wrong at the image from array. So what are we getting there? Oh, we probably didn't do like the normalization stuff here. Here we're supposed to divide by 255 here. Because we want it to be in the range of 0 to 1. Fuck. Which means that here, I guess we'll just do the division here. Because we just want it to be in like 0 to 1 space because it made training easier for us. What is it? Cannot handle this data. So what are we returning here? What are we expecting here? Our image is supposed to be a single image, probably with height. So let's say like image is equal to this. And image for comparison is equal to this. Image for comparison. And we'll just print image shape and image for comparison shape. What the fuck are we working with? What are we working with? 250 by 250. Whoa, 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 whoa. Why are these different? 250 by 250, shouldn't that turn into like a 720 by 720 or something? 1 over height, width height, 0 over width. These should both be 12, so it doesn't matter. Resize. Width times the second index and number of samples height times the... Are these like really fucked up? So we have 20 and 20. Okay, that makes sense. So we have 20 samples in each of them. I feel like I'm confused. Why is this coming out as 720 by 440? What am I passing into this function? They're 12 and 12, right? Print, sample width, sample height. Oops, these should be self-dot. 12, 12, yeah, so I'm saying 12, 12. These are 20, 20. Image for comparison, resize. Resize takes in a size of 2 tuple width height. So my number of samples of width should be 20. And I'm multiplying that by... Oh... It's because my glyph cache shape doesn't make sense. It doesn't match the height and width. Okay, so that's fair. That's fair. My height should match, like, what I should do here instead is I should calculate the sample height based off the glyph cache in my test. Okay. So here I have a width is equal to 12, and height should be renderer dot aspect character aspect times width. And here we can say height and width, which should now give us something like a little bit more reasonable for our resize image. Maybe this is supposed to be divided. No. Am I high? So print width height of the sample. So the 34 by 20, no, 12 and 7.3. Yeah, so it should be divided. What is a car aspect? It's width over height. So if I have width, I divide by width to get height. Yeah, that seems right. Which gives me... Am I high? 12 and 0. Oh, it's, sorry, width over renderer car aspect. There we go. There we go. 12 and 19. Great. Okay, so this gives me like an image that's like, the resized image is like approximately reasonable. Okay, good. Shape must be tuple of ints, but found type float. So here we need to floor this guy. Sure. And now we're back at the same error that we were at before. So now I have an image that's 468 by 440. That makes sense. And it's just when we're trying to write out the thing to an image, he doesn't like that we're trying to take... Oh! I'm an idiot. This whole time, all I need to do is write data I. We were trying to cast the whole array of images, but we only wanted to look at one. There we go. Okay. So now we should have in our working directory, all of this was just to see if like the samples that we got were kind of sane. So let's look at like 248. That says that it should be this character. Okay, let's look at like 257, something that's like a little more sane. Or anywhere from 245 to 237 should be like pretty bright. 245, bright. And then let's look for something like dark, which would be like maybe image 31. Right, because we see like a pretty dark character there. Or 11 is pretty dark here. 11's pretty dark here. Okay, so I think this is probably working. Right, we see like 0, pretty bright. 1, 2, 3, 4, 5, like kind of like increasing in darkness over here. Through to 12. So I think that's like, that looks pretty reasonable. You know, if we were being good programmers, we would check a little bit better. But that seems like, I think it's probably right. Right enough. Right enough to try it. Okay. So now what we can do is in our sampler here, we have a way to get a sample from one image, but now we want to like get many samples, and maybe we want like a number of samples. And so maybe for now, or we'll just say for n images. That seems reasonable. So we can just say for I in range n, self get sample I. We don't want to do that. We'll just do like a full randomize right now. So we'll say we want n random numbers in the range of images. So we can say like torch rand is rand int what I want? Torch rand int. Rand int. Low, high. Shape of the output tensor. Sick. So low is going to be 0. Rand int. High is high inclusive. 1 above the highest integer. 6. So we can just say self images len. Nope. Len self images in this language. And the shape is going to be n. So then we should say sample IDs is this. And then we say for I in sample IDs, get sample I. And we just put those in a list, I guess. Sure. Oh, I guess. How do we like, so each of these is going to return something that's like n samples of the same height by width. We're going to say like data labels is equal to this. So this is going to be n height width and n by score. And we want to like push that into something that we're going to return by, this isn't n, sorry, this is like n1, we'll call it. And then we need to push those into like an n2 height by width and n by 2 samples. So I don't know if you want to like extract those out. Can you like torch concat? That sounds right. Put two things back to back. Concatenates a given sequence of seq tensors in the given dimension. So can I like make a list of these guys? Yeah, you can. So we should be able to say datas is equal to this, labels is equal to this. And then we should be able to say datas dot append data, labels append label. Sorry, we'll call this label. Or sample labels maybe, because it is plural. Well, sample labels, boom. And then we should be able to just say return torch cat data and torch cat labels. Yeah. Sure. And assert n is greater than 0. Sure. So now we should be able to go into our test script again. And now we should be able to say, instead of getting a single sample, we should be able to get samples for 10 images, right? And hopefully nothing crashes. And it does, obviously. Why wouldn't it? Rand int received an invalid combination of arguments. Expected got int and int. Expected int tuple of ints. Oh, okay. So the size just needs to be like a tuple like this, probably. Okay, 6, 7, 8, 9, 10. So it did load 10 images. Boom. Cat tensors must be a tuple of tensors, not tensor. Tensors position 1 must be tuple of tensors. Oh, oops, because this should be datas. That's what it was. That's what it was warning me about earlier. 7, 8, 9, 10. Okay, so that gives us 2,600 samples at 19 by 12 and 2,600 labels, which means probably we could try training with this and just see what fucking happens. It's probably gonna be slow as fuck. Right, we saw that generating 2,600 samples was like painfully slow there, right? Like painfully slow. So I actually don't think that training with this is gonna give us anything reasonable right now. And we are like over time from our usual stream. We're at 2:12. So I think we'll come back tomorrow and try to optimize that a little more. Maybe we'll swap out the images for ones from a data set if I manage to download one overnight. But otherwise, I think our progress there was pretty sick. Like the highlight of the stream was definitely seeing what was it? If it was a visualized or a benchmark. It was this. It was this test.png. It was pretty sick to see that our like neural network trained on just one image came out here, and it was generated like fucking fast, right? Like it was sick. So I think we're definitely like on the right track. And so all we got to do is kind of like polish it up a little bit to make sure that we have like a good variety of training data, and then we'll see where it gets. So thanks for watching, guys. If you liked what you saw, I stream most days at around like 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you miss a stream, there is a YouTube channel linked in the Twitch description, and it has all the VODs. Go up there. There's a GitHub link in the Twitch description, and this project is there somewhere here. Today's code will eventually get up there in some way, probably, but I don't know if I'll push that. I don't think anything today was like too urgent to get into the project, so it might be a day or two. If you're watching on YouTube and you want to come say hi, ask questions, tell me I'm stupid, whatever, there's a Twitch link in the YouTube description. And other than that, have a great day, guys. See you tomorrow. Bye!